preferably using the random sampling method. And we want to find out, we want to know that if there is a connection, let's take an example of literacy versus fertility. Okay, so we know that as the literacy goes up, it has a negative effect on the fertility. So, and that has a nice logical explanation that why the literacy has a higher literacy has a low fertility rate. So, but when you go for collecting the data, we are not we are actually collecting each observation independently, right? We're not the informations of the literacy is not depend on the informations of the fertility, right? So there is two different information that we're collecting from a unit body, and later then we come up that sampling process is an observed minus expected value. That's your error. So if you take those error and then do a histogram, it should also look like a Gaussian curve with a mean 0 and standard deviation close to 1. The fundamental maths behind the regression is to minimize that sum of square error. So that's our error that we are actually looking into, yi minus y hat I. This y hat I is your expected value, and we would like to minimize the sum of this error, square error, and in due course of minimization of that error, we have an optimal estimator, and that estimators are beta 0 and beta 1. Okay, so these are the two coefficients of the linear functions that is similar to y is equal to a plus bx, right? Instead of a plus bx, I just replace it beta 0 plus beta 1x. Okay, so it's kind of, this line is kind of intuitive in a sense that if you just slide down this blue line to the lower half or to the upper end, lower end or the upper end, in both ways, in both of these two situations, you get MSE which is quite high, but the MSE will be minimum if we pass this blue line right through this point. So that was an idea that if I ask you that, just take the do the things graphically, right? So you take every x point and you take the y point here, read the y point here for every x point, and then take the offset from of the point that is falling on this blue line, and take the and use its pair with this black dot, measure the difference, take it square, and then do it for all other pairs of point, and find out the MSE. So if you could do that for using a line which is passed through this lower end or passed through this upper end, you end up with a high MSE. But if you just pass the line through this data cloud, you suddenly get the low MSE. That was an idea, right? MSE, mean sum of square error, must goes to 0 or as minimum as possible, and that's why the idea is called least square error. It's called OLS, called the ordinary least square error. That was the assumptions that is running behind these regressions. Okay. So in order to, so we have two coefficients, that is beta 0 and beta 1. In order to find out which beta 0 and beta 1, I mean, just before looking into that equation, so this is essentially a straight line equations. Y hat is equal to a plus bx, or beta 0 beta 1x is the equation for a straight line, right? So what would be the coefficient value a and b, or beta 0 and beta 1, for which I will get the MSE as minimum as possible? That was the central idea of regression estimations. Okay, so and that goes to a classical idea which is called linear optimization problem. Okay, so consider these coefficients beta 0 and beta 1 are the weight parameters, right, or the parameters of the regression function. It's a two-parameter functions, beta 0 and beta 1. And we wanted to find that at what beta 0 and at what beta 1, the error, which is written in the y-axis, which is called as the cost, goes to minimum. Suddenly, if you start moving from this point to that, right at this point, stop here, we get a minimum cost value. And that suggests that you get the minimum error at a beta 0 value, which sits there. And if you do the same things for beta 1, we can then able to find out which is the what is the beta 0 and beta 1 value for which I get the error as minimum as possible. So this is this idea is called the gradient descent algorithm. It basically tells you this black ball is basically, if you just release that ball, you just roll down here, move a little bit, and then come back again, and gradually it settle down right here. Okay, so if you just imagine that each point, if you just make a tangent to each point, you find that right at this position, you have a tangent which is flat. This tangent means you have a slope, right? That means if you consider this weight as x and consider this cost as y, for every point except this, we have delta y over delta x, change of y over change of x, and that is non-zero. It could be negative, it could be positive, but certainly that is a non-zero. So when you do that at this point, when the ball actually rests at a minimum energy level, if you draw a tangent, we get a delta y over delta x is 0. There is basically no change in x and y. Okay, so in that, and that's the point where we're actually looking into. That point is basically the point where the corresponding beta 0 and beta 1 will give you a best solution where you can get the minimum sum square error, and that point is called the global minima. Sometimes it is called local minima, depending on how curve is actually bending. So looking into I'm not sure that whether you'd be interested in looking at the mathematical details, but here is a fact, just some of the curious minds. I just put this slide there. So you have our actual observations, and this is our expected observations, and that's our error, some of the errors, right? So we need to find out, at what beta 1 or at what beta 0, the sum square goes to 0, okay? So delta error over delta beta 1, which is the coefficient, is the slope value, equals to 0. I just make it equals to 0. That's how the linear optimization problem works. And then I use a first order power rules, first order derivative equations using the power rules to make the solutions here. So if you use the power rules for the first order derivative, this square comes here, and we have to subtract 2 minus 1 from the square. So what we get 2 sum of yi minus y hat, 2 minus 1 is 1. And then if I just do a simple mathematics, 0, bring the 2 to the right hand side, 0 divided by 2 is 0. And I then multiply summation signs to every term. So I'm going to replace that y hat to the corresponding expression, that is y hat is equal to beta 0 plus beta 1x, or a plus bx, and then just simply multiply the summation term with every term inside this bracket. So summation of yi minus beta 0 is summation of beta 0 minus sum of beta 1x equals I minus beta 0 n, because n is, this is a constant, sum of 1 is basically n xi, and that's give me a nice looking normal equation for solutions of these linear functions. Okay, so you're going to find another auxiliary function. This is a normal equation 1, and we write for which is this. So only the principle remains the same. I have just only multiplied one x factor with this one, and this gives me a second normal equations. And without those simultaneous equations or auxiliary equations, we cannot find the solution for beta 0 or beta 1. So once we equate them each other, because this is also 0, that one is also 0, so we can equate them each other, and we can eliminate the term to get the beta 0, either beta 0 or beta 1. It's pretty easy function. Okay. In another way, we can divide the whole term, the term that we have seen earlier, right? This part, so summation of y minus beta 0 n, this part. If we just divide this whole term by 1 over n, just take the multiplication of 1 over n to the left-hand side and the right-hand side, what we get, summation of yi over n minus beta 0 n over n minus beta 1 summation of xi. And that gives me y bar minus beta 0 minus beta 1 x bar. That suggests that if you know the beta 1 from the previous two auxiliary equation, we just plug it here, we get the beta 0. So that's the mathematical idea of deriving the coefficients, two coefficients from the auxiliary functions. And there is another way that we can quickly understand that what exactly, how could we quickly find out the beta 1 value? Well, it goes to the idea of the variance sharing, right? So imagine that, look into this right-hand side, right? So we have a variance of x and a variance of y. And the variance, I'm pretty much sure that variance is, you know about the variance. Variance is something which is of a data, right? So that's a equivalent to the standard deviation. Just the standard deviation is the square root of that variance, right? So the standard deviation is basically suggesting is that what is deviations from the mean, right? So the statistician often call that variance as the energy stored within the data. So, or in other words, the information stored within the data. So imagine that we have information stored within the x variable is this, information which is stored within the y variable is this. So if you imagine this situations where x and y are sharing at least 10% of their information to each other, but if you consider this lower one where the information sharing is much higher, more than 80% of the information, both of them are sharing with each other. That means if I now develop an equation, that equations will explicitly explain more than 80% of the variance of y as a function of the variance of x. And that's kind of an intuitive idea that y, if you consider the ratio of variance of y over variance of x and multiply it by their correlation, this will be pretty much similar to the beta 1 value, which we can get from solving this previous normal equation, previous auxiliary equations, right? Okay, so once we have those two coefficients in hand, we now have a unique problem that's called the problem of inference. So we get our data through the random sampling process. We find the beta 0, beta 1 value from the existing data. And that's, we can say that that's optimized results called the best linear unbiased, because we follow that norms that where we can get the minimum sum square error. So we can say that, yes, we have a line estimate, which is what you call the mean estimate, right? Mean of the distribution. Why the mean of distribution? Let's look at this mean estimator. So this is a hypothetical scatter diagram where you just take a vertical slice of all those 4 locations and then take the data of all those vertical slices and try to do a histogram. You find that all of the histograms sort of looks like this, and the line is actually passing through the peak of this histogram. And these histogram peaks are basically suggesting you where your mean is, right? So that's why it is called the mean estimator. Now the problem of, and if you look into this 3D diagram where I just explicitly showed you that in the z-axis we measure the probability, and mean for a normal distribution, mean has the highest probability. And you can check back your basic statistical class that what is the highest frequency that you observed for a normal distribution. That's always be mean. So therefore, the mean has the highest probability, and the line, this regression line, is actually passing through that mean estimators, right? So now that we have a mean estimator, the problem of inference suggests that what happens if you change the data? What happens if you have a new set of data with the same function? Or what happens if you have a new set of data pursuing the same problem? Do we really get the same beta 0 and beta 1? So answer is no. Since beta 0 and beta 1 depends on the observed value, sample value, as the sample value change, beta 1 and beta 0 both change. And it keep on changing and changing as long as you keep on changing the observations. So what is the way out? Are we inch closer to say that this sample-based regression estimator, this is what I call the sample regression estimator, not the population regression estimator, because it runs based on the sample value. So this sample regression estimator, are we happy enough with this sample regression estimator? Certainly not. We cannot say that with full confidence that this would be the population estimator if we really do a lot of experiment, right? So we cannot say that. If you do a repeated experiment, this would be the population estimator. We cannot say that because the estimator is supposed to change as the sample value change. So what happens? The statistician by that time suggests that instead of point estimator or the mean estimator, what if we just go for an interval estimator, right? So they're going to find out the standard error of beta 1 and standard error of beta 0. Both could be easily found from the existing matrix, and then just subtract the standard error from the estimated beta 1, make that the lower boundary, and add the standard error of beta 1 to the computed beta 1 to find out the upper boundary. So now that we can say that we have a lower boundary and we have an upper boundary within which true beta value could be found. Now, and this the same logic could be applied to the beta 0 as well. And I should mention here that why we are actually trying to find out the true beta value, and we need to impose, we need to find out, we need to actually understand that the one additional hypothesis that what is your assumptions, right? What was your assumptions? So if you're working with, let's say, fertility and literacy, my assumptions would be that the literacy has a profound negative effect on the fertility, where I have a counter assumptions, which is called the null hypothesis, that suggests that no, literacy doesn't have any profound effect on the fertility, right? Whatever your effect you are anticipating, it just happened by chance, okay? But we have our alternative hypothesis suggests that no, literacy have a profound effect on non-zero effect on the fertility. So if we stick to this sample regression function, which depends on the sample value, and if you keep on changing the sample value, this will change. So we're going to find out the lower limit and upper limit within which we can say that now that we have estimated the lower limit and upper limit, we now can say that this would be the range within which the real beta 1 or beta 0 value could occur, which is kind of representing the effect of literacy on the fertility. But again, the problem still the problem still hasn't solved yet because of the fact that standard error is actually which is this. So we have a variance of beta 1, which depends on yi minus observed estimated value divided by n minus 2. over sum of xi minus x bar. So that's your variance. And then if you take the square root of variance, you get a standard error of beta. So since your standard error actually depends on the observed value, even if you change the, even if you compute the lower limit and upper limit, your sample observation change, your lower limit change, your upper limit change. The problem still persists. Then scientists, the statistician thought that why don't we use a standardized distribution, right? A standard theoretical curve. So theoretical, the advantage of using a theoretical curve is that, excuse me, is that for every theoretical value, we have a fixed probability value. And even if your sample value change, the transformed theoretical value will not change. For a given theoretical value, we have a fixed probability level. So therefore, the statistician has a genuine idea that why not we use the t distributions or the z distribution in the regression function, which can give us a sort of solid theoretical basics to solve this puzzle. So once we introduce, that's the reason why we need the t distribution introduced in these regression problem. Okay, so once we convert our estimator into t value, so we have our estimated beta 1. If we convert that beta 1 into t value, just simply divide the estimated beta by the standard error of beta, we get the t value. So once we get the t value, we now look into the t value distributions, which where the standard under the standard t distribution curve, the negative 1.96 to positive 1.96, this is the limit which is under the null hypothesis, which assumes that no, there is no effect of literacy on the fertility. But we have 5% area, 2.5% this side, right hand side, and 2.5% left hand side, which suggests you that yes, these are the two areas where if your t value is falling in these two areas, we can say that there is a significant effect of literacy on the fertility. So now that we have structured that problem in a way so that we can transform the actual value estimated, the sample regression estimator into t value, by looking at the t value and corresponding probability level in the y-axis, if your the probability value in the y-axis corresponding to t value is less than 0.05, which is a sort of standard statistical significance test level. If your p-value or the probability level corresponding to that estimated t-value is less than 0.05, you say that no, whatever I estimate through this sample regression function is a statistically significant, and that is, we can say that it is significantly different from zero. Okay. That means if I run the experiment 100 times with a different data sets, with a different, by changing all observations, right? So if I run the test 100 times, 95 out of the 100 trials will guarantee me that it will end up with a non-zero regression estimator. So now that we have this structure in these things, it gives us a profound statistical logic that whether your beta 0 or beta 1 is statistically significant or not. It sometimes happens that we have a significant beta 1, but we don't have significant beta 0. It sometimes happens that we have a significant beta 0 intercept, and we do not have a significant beta 1. It could happen. Since we are actually dealing with the effect of x and y, we are mostly concerned about the beta 1, which is the slope value of the regression line, that is delta of y over delta of x. So once we introduce that t distribution table into the t distribution function into this structure, now we have a interval estimator instead of mean estimator or the sample point estimator. We have interval estimator. The way that we could estimate the interval is that just subtract the t alpha over 2, that is 0.05 over 2 times the standard error beta, and beta 1 plus 0.05 over 2 times standard error beta. So we have a upper limit here, we have a lower limit here. The same could be done for yeah. So the lower the t value at 0.05 is 1.96. So we have to subtract this product from the estimated beta, and we have to add this product from the estimated beta to get the lower limit and upper limit. So interestingly, once we have a statistically significant beta coefficients, this lower limit and upper limit will not include zero in its range. So what happens if I have a insignificant beta 1? At that time, if you compute the lower limit and upper limit, which is called the 95% confidence interval, you get a value which range from negative to positive. That means it has a zero in its range. And that is another way to check that whether we are going in the right directions or not. Even if you fail to interpret that, just looking at the interval lower limit and upper limit, you can see that whether the range is actually including zero within its range, okay, within its lower limit and upper limit value. The same could be done for the intercept. We're gonna compute the variance of beta 0 using this process. Take the variance of beta 0 to compute the beta standard error beta, transform the standard error beta into t of beta, and we're gonna do the same process for that. Okay. So I'm gonna take a example. We have a precipitation in the x-axis. We have a temperature in the y-axis. We know that as the precipitation goes up, temperature goes down. That's follows the normal rules. So I'm going to take some example from the R Studio. This is synthetic data. Really doesn't relate to the actual observations, but we have some synthetic data, and this suggests that once you have, let me just, okay, so that's a better way to look into that. So we have this functions, the coefficients. This is our beta 0 intercept. This is your beta 1, that's the slope. So we have our estimate. Intercept is 171.75 millimeter, and the slope is the intercept is 171.75, and the range, the beta 1, which is the slope value, is negative 0.49488, which suggests that if the 1 millimeter precipitation has increased, temperature drops by 0.49488 degrees Celsius. Okay, and this is just the intercept in terms of the degrees Celsius. Okay, so we are actually looking more concerned about this fact. So if we divide this estimate by the standard error, we get t value. Divide this estimate by the standard error, we get t value. And once you get the t value, this system is actually looking to the standardized t distribution table and picks up the corresponding p value. In both of the cases, we have a statistically significant estimates. This suggests that if you run the experiment 100 times, 95, I mean, this is significant at a level of more than 99%, right? So this is your this is your more than 99% confidence limit. This is your 99%. This is 5%. This is 90%, right? So it suggests that if you run the trial 100 times, more than 99% guarantees that it will end up with a non-zero coefficients. Okay, so we can say that the estimated beta 1, which suggests that what is the effect of rainfall on the temperature, is certainly the non-zero effect. Okay, and these are the parameters which we can consider as for the total variance explained. That is 34.43 is the percentage of the variance that this function is actually explaining. Okay, and there is a nice connections between these estimates. So we have our estimate this. So imagine that what happens if I have a high standard error. So if the standard error goes up, if the standard error goes down, since we are dividing this value, estimated value, by the standard error, if the standard error goes up, the t-value goes down, the p goes up. If the standard error goes down, the t-value goes up, the p-value goes down, and we have our statistically significant estimate. So so the next part is what happens if you have something. What happens if we have a complex data? What happens if we have a non-linear relationship between x and y, which is shown like this? So this is a linear functions, linear relationship, which is pretty much simple and straightforward. We can fit a straight line. But what happens if we have a curvilinear functions, something like this? Then we have to bend that straight line, and we have to find out a curvilinear function. That's the polynomial functions, right? So it's a specialized case for is linear functions, where we can look into this estimated y is a function of a second order term, which is square term. So this is our second order polynomial function, beta 0 plus beta 1 x plus beta 2 x squared. If we have a more complex function, we can move to the third order functions. So might be this is equivalent to, might be this is not a third, but another bending could something like this could give you a something like this. I'm sorry. Something like this could give you the third order function. Okay, we can actually bend that regression line. Trying to touch each point. So we can goes up to ninth order polynomial function, extremely complicated functions. But that ninth order complicated polynomial function is not allowable for the problem that we geographers are actually dealing with on a daily basis. Okay, and why it is not why it has not been or why it is forbidden to use in the spatial studies. It is because of that they are pretty much complicated to interpret. I mean, the easiest one to interpret is the linear function, because it simply suggests what is the first order effect of the x and y. At max, you can go to the second order. What is the second order effect that you are anticipating between x and y? And that is 2 beta 2. And if you do, and why 2 beta 2? That is if you let me just, if you do a first order derivations of this function, it ends up with 2 beta 2, taking this power as before. So that's your rate of change of y as exchange by 1 unit. So we're going to find out to find out the optimum beta 0, beta 1, and beta 2. We're going to apply the same rules, finding out the linear optimization principle, equate them equals to 0, and then find out what is the corresponding beta 0 and beta 1, where we can find out the best possible solutions, right, to get the minimum sum square error. Okay, so what happens if the scattering is more complicated, if the scattering gets more complicated? So we start with something linear, then I talked about the curvilinear. Now that we have a more complicated response, it's you cannot find any pattern as well, right? So we have a some x and y, but we certainly do not have any linear or curvilinear. It's just a cluster point without having any sort of relationship. So what happens to that particular situations? What model should I use? It sometimes happens with all of us, right? So we are nowhere. We cannot find any appropriate or adequate solutions if I end up with such kind of clustering where the fitting a linear function is pretty much difficult. So we're going to think about then we're going to think about the data-driven approach, and the data-driven approach is the core idea of machine learning, right? Now I'm going to move from these simple regressions to the gateway, to the doorstep of the machine learning. So let me just confirm that up till now, before we jump to the machine learning stuff, did you follow me? I mean, if you have any questions. So if I'm just asking some of the curious minds, if you have any questions, it really doesn't matter whether you're not familiar with mathematics, really doesn't matter. If you have any questions, please let me know. Or am I moving too fast for your understanding?
Okay, anyone any question you can ask?
I'm gonna move to the next part, machine learning part, but let me just get a confirmation that whether you have followed the first part or not.
So no question, I think. Sir, you should continue your next part. Okay, any question you can write your chat box. Okay, after complete the second.
Sorry to interrupt you. Even if you feel that I'm moving too fast or my pronunciation is not familiar with you, I'm quite happy with all of those comments, right? आपको अगर लगे कि मैं बहुत जल्दी बोल रहा हूँ, then you can stop me, right? And interject me and.
It's okay, sir.
Right?
It's okay.
Okay, then. Visible now? I'm hoping the screen is visible,
yes,
right?
Yes, it is visible.
Right, okay.
Yes, it is visible.
So from that part, from that basic knowledge, I'm going to move to these the debate of the machine learning, okay? So the core idea of the data-driven approach is learning through the data. So this is a classical example that we have some dashboard data, and there's two person is actually having conversations that we have a conversation. Do we trust this data, right? So the person says that yes, that's come from the real world, and we need to apply some sort of analytics to make it more comprehensive, right? So the whole idea of the data-driven approach is it's quite simple. In fact, and you know that it really doesn't require all those sort of assumptions, statistical assumptions that the linear regression is having. And it's quite simple, based on the simple principles that whatever data tries to tell, the model is actually picking up that story. If you change the data, the model story. It is totally data dependent. It really doesn't require any sort of assumptions, parametric assumptions, the assumption that we required to run a linear functions. And that assumption is that both x and y should follow the normal distribution. We don't need that kind of assumptions in the data-driven machine learning model. Okay, so it's called the recursive partitioning of the input vector space and optimize the estimation through minimizing the error. So these are the two things that learning through the data, recursive partitioning of the input vector space, and optimize the estimation through minimizing the error. So these are the three things that we need to keep in mind, and I'm going to unfold all of those things, see three things gradually, okay? Let's just concentrate on the images that has been given in these slides, okay? So the learning is a unique process which you all learn. In fact, right now in this classroom, you're learning from my speech. So we'll look into these first interactions of the baby's mind with his or her surroundings. So there is some examples that this baby is trying to touch the flame, this flame, trying to know that what exactly it is. And as soon as its hand is touching this flame, his brain gets a signal that this is warm, it should not touch it. So brain gets a information, a data from these actions. Okay, so when the baby tries to stand up with its feet, there are hundreds of times that baby falls down. Okay, the baby might not succeed with its first step, gets the signal that which are while I'm trying to stand up. So brain tries to avoid that ways and find out the most suitable ways by which it can stand up on its own feet. When it tries to slide down, the first attempt, the brain is quite in prior knowledge of how to slide down through a slider. So once the baby tries to slide down first attempt, its brain gets information that now this is how we have to slide down. It's not that I have to bend my head in the front, but I have to lean my head back. Bend my head in the front, but I have to lean my head at the back, so that I can have a nice sliding posture. So, and then the best example is that the driving school, right? So, I always had a fear that if I sit in front of the driving wheel, I might hit somebody else, because I don't really have the bonnet size. What is the minimum size that is required to pass the bonnet while driving through the road? I had always a fear that the moment I sit with the driving wheel, I might hit someone. But that fear gradually lowers down as long as more as I drive. That the bonnet size is gradually more precise into my eyes, into my brain. So now I have a clear vision that yes, this is the space through which my bonnet can pass through. So the brain is actually getting a lot of information through the interactions. Without interacting, without having interaction with the data, the learning process cannot be complete. It's all about that learning process, and that's the simple mechanism or the learning process that we can mimic in the statistical world. So it's a learning model. It's a learning that actually improves our performance. So we're going to find out some sort of statistical functions that learn from the data and gradually improve its performance. So learning model improves with the variation of the data. As I keep varying the data, more larger the variations of the data, more is the learning process, right? So the model can understand, well, this is the range within which I have to train myself. Now, imagine that you being a swimmer, if I ask you to do a rock climbing, you're not able to do that because of the fact that your brain is not trained with that. However, if you have a training of all of them, right? So rock climbing and swimming and trekking, your brain is having sort of prior information. No, I have that that sort of prior information. I can do that. So that's the idea that how these machine learning models actually, some of the machine learning models are very good, some of them are very bad. And why they are very good and why they are very bad depends on the learning process. Okay. And obviously, the accuracy depends on the range of the observations the model sees. So these four gentlemen, Bremen, Friedman, Oslin, and Stone, in 1984, developed the first basic mathematics of a machine learning model. And that's called the classification and regression trees, right? So there is this regression trees is nothing related to the regression function as well. They coined the name just to apply the functions over a continuous variables. So we have two kinds of mathematics. One is for this classification trees, and one is for regression trees. We're going to come to each of them one by one. So, as I pointed out before, that this is kind of a sort of recursive partitioning of the input vector space. So when I'm saying the input vector space, you can imagine that there are a lot of variables, and a handful of variables make up the input vector space. Okay, a combination of different variables make up the input vector space. So if I partition that input vector space recursively using sort of independent vector, if we partition the dependent input vector space based on the independent input vector space, okay, I can have a kind of binary trees, right? Where the we have a conditions here, and we have a right side node and a left side node. The right side node is sort of suggestion that has been satisfied at this positions. If the observations satisfy the conditions, it goes to the right node. If not, it goes to the left node. So we have a sort of binary classifications using that thing. So here is an example that I'm going to take. I have taken the classical example that they put up in their paper. So we have a binary classes, absent and present. So, it's a presence of hepatitis within a patient. Okay, so 0 is absent, 1 is present of hepatitis. And I'm going to use the example uses a two additional factors. It's called the blood factor, protein in the blood, and alkaline phosphate in the blood. These are all blood samples. Okay, so protein and alkaline phosphate, these are two variables, right, which can appropriately explain the presence of hepatitis B, presence of hepatitis or within a in the body of a patient or not. Okay, so just that the protein picks up as the first splitting criteria. The first partitioning of the input vector space happened by the vector called protein, and a threshold value of negative 45.43 has been picked up. The question is that how the system will pick up that protein variable instead of having two variables, alkaline phosphate and protein. It picks up the protein Y, and even if it picks up the protein Y, 45.43 has been taken as a threshold value. It suggests that all of the observations belonging to this hepatitis patients, where we have a kind of binary classes, absent and present, if the protein is less than 45.43, then goes to the right side, and if the protein is higher than 45.43, they go to the left side. Okay, so the question is that first is Y protein, second one is Y 45.43. Why not any other values? It goes to the idea that if I use that value, I mean, if I can start with all values, right? Start with the first observed value of protein and the last observed value of protein. And after trying all of these values, the value for which I get a minimum impurities in these right-hand side classes. So the right-hand side class is suggesting that if the protein value is less than 45.43, it goes to the right-hand side. And it gives you that a sort of classes where how many of those of the total, how many of them are actually hepatitis A and how many of them are actually hepatitis B. How many of them are having have a hepatitis? How many of them doesn't have hepatitis, right? So the present and absent. So this node is actually capturing the Guinea impurity through this process. So if I picked up less than 45.43 as a threshold, it gives you a Gini impurity at descent, which where pi is the probability of correctly classifying the category, and 1 minus pi is the probability of incorrect classifications. So if I have a higher probability of classification at this value, 45.4, less than 45.43, and if the Gini impurities for all other protein values are higher than this 45.43, then I'll pick up 45.43 as the best splitting criteria for which I get the minimum Gini impurity. Impurity means nearly all of the classes are pure. It could be present, it could be absent, it could be hepatitis B present, it could be hepatitis B absent. Most probably it is hepatitis B absent, that is all zeros. But the probability, the Gini impurity should be minimum. Impurity higher means there is a high chances of mixing of present and absent, hepatitis present and absent. But if I reduce the chances of either present or absent, I have a pure classes. So out of all possible protein value that lined up in my input vector spaces, 45.43 is the best splitting criteria for which I get the minimum Gini impurity value. Now, the one which is greater than 45.43 goes to the another left-hand side and it passes through another set of criteria. The next criteria is this, right? And it keeps on doing like this, splitting the space into the vector space into more subclasses until it finds the minimum Gini impurities. And the question remains, the why protein, why not alkaline phosphate? Imagine that I have tried all the values of protein, find out the impurities at descent. I have tried all the values of alkaline phosphate, the Gini impurity at descent. The one for which I get the minimum Gini impurity, that should be taken as the first splitting criteria. In this case, we have protein value with 45.43 as the value for which I get the Gini impurities minimum as possible. That's why it has been taken as protein less than 45.43. Okay. So here is an example of elevations and flood frequency. We have three kinds of flood frequency: 1, 2, and 3. One is every year flood, once in every year. Once in 1 year, once in 2 years, and once in 3 years, right? So that's the flood frequency that we are actually trying to map as a function of elevations, right? So you have I showed you that's just a simple two regression classification tree. So it all uses the different elevation value. So all are elevations, right? So at different elevations value, we have classified them and find out the classes. Okay, so we have 1, 1, 2, 1, right? So this suggests you the number of observations falling in each of these leaf. This is called the splitting node. This is called leaf. So this suggests you the probabilities of correctly classifying the class 1, class 2, and class 3. Okay. So now that we have a classification problem, can the same be applied to the regression problem? I'm not dealing with the classification problem, but I am more interested in what you call the dealing with a continuous variable regression problem, right? So the answer is yes, we can do that. Instead of using this Gini impurity function, now the criteria should be residual sum of square error, RSS, where this y hat, it's not actually similar to what we get from the regression function, but it's y. In this case, y hat is basically the mean, right? So if I get deviations of observations from its mean, right? Take the square and take the sum. The value for which I get the minimum sum square error, the variable and the value for which I get the minimum sum square error, that variable of that particular value will be picked up as a best splitting criteria. Okay, so let me just go to these next slide. So a node will be split based on the minimum residual sum square error. All observations in the dataset will be tested, and to get that minimum sum square error, the same principle. Every observations in that data table will be tried, and the one for which we get the minimum RSS will be picked up as a best splitting criteria. And some of the right node and the left node should be less than the sum square error at the total. So before splitting, what we get? Before splitting, we still have RSS. Before splitting the space, we have mean of y, we have and then if you just compute the mean deviation, that is square and sum it, it must be it should be called as total sum square error. After splitting, after applying the splitting criteria, we have right side node, we have a left side node. If you sum this RSS left and RSS right, that sum of these two must be less than the sum of the sum square error for the total, which we can get before splitting the nodes. So here is an example. We have, let me just make it a bit large. So we have a problem. It's a prostate cancer. So we have a prostate weight and the cancer volume. These are some of the splitting criteria based on which we can try to build a regression tree, right? Based on the continuous variables, we have a log of the cancer volume, LCAVOL, and we have prostate weight, right? So if I apply the criteria to understand the probability of prostate cancer, it's not a binary classes, presence or absent, but it suggests that what's the probability. The prostate cancer probabilities will goes up, has a close linkages with the prostate weight and the sort of cancer volume. So the prostate weight and the cancer volume are the two variables. We just transform their actual observation into the log form. So log of the prostate weight and log of the cancer volume. These are the two independent variables. Now let's make up the input vector space, and we have a dependent input vector space that's called the probability of prostate cancer. So if I use the log of the cancer volume as a first splitting criteria, right? So we get an RSS value. I'm sorry, I guess, yeah. Okay, so yeah. Sorry, log of the cancer volume is our dependent variable, and the log of the prostate weight is our independent variable. So it suggests that if I take the log of the cancer volume as 1.05, something here, I get a residual sum square error which is low, which is like this. If I take any other value, right, log of the cancer volume, I get a RSS value which is exploding, either this or that. So the first splitting criteria is 1.05. So the input vector space has been split into two parts. The next splitting is this. So if this is your next splitting. Now check up the RSS value, residual sum square error. So if I pick that, we have we have a next optimum splitting is negative 0.048, which is this, right? And if we keep on doing that, right, the next splitting would be this, okay? Next splitting would be this 2.79, okay? So we have 1.05, negative 1.48, and 2.79. Now, this is for the log of the cancer volume. Now, if I check the log of the cancer volume, the what do you call prostate weight, right? We get a RSS value for the prostate weight is minimum is this, right? And which is 27.75, and we get a RSS value for this one is 25.11. Certainly, this 27.15 is higher than 25.11. Therefore, the best splitting criteria would be 2.79. That's this, okay? And if I keep on doing like this, splitting the space into more subspace like this, right? I can make up a nice decision tree, which looks like this. So we have then have a regression tree, which looks like this. So you start with log of the volume, then the next splitting criteria is this, and likewise we built a nice regression tree. Here is an example of soil parameters. So we have zinc as a dependent variable, variations of zinc from a river channel as a function of elevation and distance from the river, right? So zinc concentration as a function of elevation and distance from the river. And we're going to apply the same RSS rules, minimization of the residual sum square error. We tried first with the elevations, each observation of the elevations and each observations for the distance from the river, for which we get the minimum sum square error. That value has been picked. So once we just try to look into that, because picks up a set of observations, build another tree, make it estimated value, go to the data set again, build another tree, and make it predictions. So likewise, for it builds nicely looking aligning a cluster of the data points that we are actually looking for, and that's the core idea of the random forest regression. Okay, it could run both on regression and classification as well. Okay, so the difference between there is a slight difference of the outcome of the machine learning random forest and classification regression tree. The one is that when it gives you the outcome of the classification, so each tree will give you the majority votings. That means if you look into the each leaf at the end, how many what is the majority vote that has been falling in each leaf. So if I have 3 classes and one of these 3 classes has the highest voting, it picks up that classes belonging to this leaf. Okay. However, if problem outcome at the end leaf